Testing's already. What about can you believe that?
Let's start with a couple of just quick announcements. So originally on Monday, we had our first test. You guys was scheduled for Monday. I moved it because first I was going to have it on the mass day. And I had a feeling that just felt like this was a mass that was going to run long, and I didn't want it to be a rush. And just we'll start the next set of stops on Friday and Monday. Would not be part of the test. We're just going to start the next teach, and we'll do the test the following period, so that everybody has like a regular full class period to do it. Now I know it's homecoming week and that stinks, but I don't know. Nobody should be complaining too much about the test getting moved back or a period, right? It's usually a pretty easy sell. All right. So today we're gonna knock out the last section. Thank you for this before the test. Before I do that, though, do you guys have questions on stuff, homeworks or whatever that we want to talk about?
Is this for the delta math one?
Sure.
When we had to finish the analytical limits one?
Yes, that was for Sunday.
It's called last Sunday, right?
I don't remember.
Or whatever it was.
Some point. If I've graded it so far, marked it missing, then it was supposed to be done. If it hadn't, it wasn't. But everybody has a weaker grade, so like we screwed up the dates. I apologize.
Can you go over one of them?
One of the types of problems?
Yeah.
Sure. And then last time we added another delta math, right? Did you see that, Lucia?
I think so. I mean, I think I got all the ones that I needed to do because I checked, but.
Okay.
I have a question, kind of like show you after you're done with.
Yeah. If it's like a super individual one, maybe we wait.
Okay.
But if it's a homework one,
Yeah, that
so you want that? Okay.
Or was it the IJ and ST one? What?
Well, this is what we did last class.
That's what I was going to ask you about.
Okay.
Because I think did I do it? Or was it the squeeze theorem one at the bottom? Because we weren't supposed to. Yeah.
You can do this by now.
It was that. Okay. Okay, so I'm just confused on what I had to do.
So this presentation is like the easiest presentation you can get of a squeeze theorem because it's already given you the inequality. If you have to build this yourself, that's a little bit harder. But if it's given to you, all you need to do is check the limit of g as x approaches -2. And since that's a polynomial, I can just direct substitute it. So just plug the -2 in. And then check the limit of h of x as x approaches 2, or -2. And again, polynomial, so all I have to do is plug that in. So like -28 plus 11 is -17. Here I'm going to have -16, or that's 4 times -16 minus -8, -20, and then, or plus 8, sorry, so that's -8, and then minus 5 more is -13. That was -17. They don't agree, so that tells me nothing, right? Can't do that limit. There's not enough. Oh boy. Well, then I just did some arithmetic wrong. What arithmetic did we do wrong here? 28, that's -17. I agree with that. It's -16. Oh, it's 4, not 8. Look at me. We're a bunch of dummies. So it's going to be -17 then. It's what I get for trying to do stuff with no calculator at this late in the day after I've been shouting all day. I'm not really shouting, but like, I'm exhausted and certain voices starting to go. There it is. So like, this presentation is like as easy as it gets for a squeeze theorem. You just have to recognize it's a squeeze theorem problem where all I need to do is check the upper and lower limits. And if they agree, that's the answer. If they don't, I can't do anything. There's no other option. Does that feel good? Okay. Sam, did you say you had something from the homework you want to talk about?
I might.
Okay.
I can find it. It's another paper.
Okay, yeah. While you're looking, I'm going to see if anybody else has one, and when you're ready, holler at me, and I'd be happy to start. Does anybody else have something you want to talk about? Meredith?
It's a question from the homework.
Yeah, do it.
It's from the squeeze theorem for 2.3,
Okay.
number 62.
2.3, number 62. Love it. I love that you're like back here still grinding away at stuff. All right. I want 2.3, you said?
Yeah.
Oh, this is not going to work. What's the deal? I'm a stupid machine. Or maybe I won't. Just do it the old-fashioned way. You know, like sometimes technology is like a blessing, and then other times it's just like an anchor. Like you're supposed to make my life easier, not harder. I can just have my book open at my desk and write this down. You said it was 60 what now?
62.
62. Thanks. Thank you. All right, so 62. Okay, so don't think I would do this as a squeeze theorem. Looking at this, Meredith, it was just in the section, you know, like we got to some squeeze theorem problems, and you can stop. So probably the first step is to try a direct substitution, right? You try, you get 0 over 0. So what I would do next is probably try multiplying by a conjugate. The place where I'm most concerned is the denominator being 0. So I'm going to do the conjugate of the denominator, and that should probably be enough to get us there. If not, I might have to do the numerator 2, but I would start here. So if I do that, now it's tempting to try multiplying this stuff together. I'm not going to bother with it in the numerator, because as long as the denominator is going to be non-zero, I can just direct sub in the numerator and I'll just be done. And I'd much rather just leave it the way it is and do a direct substitution and try to FOIL this all out and not make a mess out of it. You kind of see what I'm getting at, right? Like, so if I multiply this out, I'm going to have 3 minus x minus 1. And if I plug the 2 in, still didn't get there, right? So, let's do we'll write this as 2 minus x, but let's multiply by the other conjugate then, and see if that clears up our mess. I think it probably will. It's probably why it's written so deep in here, is it's like a challenge kind of problem. So I'm going to multiply this one. I multiply these two parts together, right? I have 3 things multiplied together. I can choose the order I want to do the multiplication, right? In the numerator, I have parenthesis, parenthesis, parenthesis. So 3 things. Do we all see that? Make it easy on yourself. Multiply just the 2 things that you want to go together and leave the 3rd thing dangling. So we're going to have limit as x approaches 2. And then I'll have 6x minus 4.
and then I'll still have this root 3 minus x plus 1 over 2 minus x, and then I'll still have this root 6 minus x plus 2.
Do I still have to include the conjugate in the numerator?
So this guy is here, right?
For the next one.
Yep, and these two guys turned into this right here. So then these two guys turn into this, right?
Yeah.
And like this guy is here.
But wouldn't you still have to multiply the root 6 minus x plus 2 with the root 3 minus x plus 4?
If I have like 2 times 3 times 4, I can just multiply those two together and then multiply to the 3, right? That's what I have here, is just 3 things multiplied together. Does that make sense? Okay. So again, like on stuff like this, where it's confusing, right? When you look at it, like how do I multiply those 3 things together? Just see if, like, can I simplify this? What does this really look like with just like boiling it down to brass tacks? And it's like, now I'm not going to make a mistake. Like if I think about it this way, it's like, okay, I can definitely do that, because if it's just 3 numbers multiplied together, I can do what I want to do. And here, Meredith, I get that becomes the 2 minus x, and now we're good. Right? So now I can direct sub this. So that's going to be 1 plus 1, so 2 over 2 plus 2, 4. So we get 1/2. Woof. But like, not going to ask you to do it.
Okay.
Like that's number 60 whatever for a reason, right? Interesting problem. Glad we spent some time talking about it, thinking about it. In a time test, no thank you, right? No thank you. Can I, before we move on, I want to make a point here about something that I remember seeing on the homework quiz when we did these analytical limits, and I want to make a point to address with everybody. So is everybody listening? Because I think almost everybody did do a great job of this. And that is when the limit stays and when the limit goes. So in my problem, if there are x's in the expression, I still need that limit in front. When I was looking at your homework quizzes, a lot of us, the limit disappeared halfway through. When should the limit disappear? Once you've done the direct substitution, there's no more x's. Right? Look at that step. There's no limit in front of that. So the limit stays until the x's are gone. That tells me you've done your direct substitution. It's okay to drop the limit. Everybody's good? I'm going to be picky about this on the test. I mean, you can only lose so many points for dropping limits. But like that is something that will earn you a deduction if you get rid of your limit before it's time, or if you carry it past due. Okay? So again, the limit stays until the direct substitution. At the direct substitution step, the limit is gone. You guys understand what I'm saying?
Yeah.
Okay. And this is a good enough example where you're seeing this. If you go back and you look at your quizzes, did I have those back yet? Maybe I did. This one. Let me get these back to you. I think whenever you did this, or made this mistake, I made a note of it on your paper, assuming there was enough work for me to see it, right? Like, this is me saying that, like, you know, like you're forgetting your limits, you know, sorry. So again, like, take a look at my comments, because I think almost every single one of us were dropping limits, at least on number 2, assuming that you did it. So I made that notes on your papers. You did a great job. So you did. I think that was like one of the better jobs with the notation in there. So I got acknowledge that while you're sitting there. You'd be a little embarrassed by that. See your face get a little red, but that's okay.
You're blessed. You're blessed. Yes.
And I'm going to give you. And me, Sam.
I still don't know what that is. Pseudo. Pseudo is when you're like pretending you plug it in. And you have an infinity instead of actual number and you plug it in.
Yeah, that's good verbiage.
Are you still scared? Do it like that.
Okay. Sam, did you find the problem that you're looking for?
I found it, but I realized I already looked up how to do it. I think I already got it.
Oh.
Something with
That's okay. We can talk later then.
it's the thing with the brackets. Like there's like multiple equations, but it's like a piece of solution.
Oh, okay. Yeah, if you figure out like that you do want to talk about it, let me know, or stop by during community time or something. I'd be happy to go through it again. All right. 2-6 was the last set of topics here before the test. In all reality, most of the heavy lifting here is done. Okay, this is going to be, you should feel relatively familiar because we've done most of the hard ideas here already. Okay? So, what we're doing at first is defining what we mean as a limit to infinity or a limit at infinity. So, like, even though x goes to infinity, maybe the function goes to a specific value, right? We did this already. I got ahead of myself in 2.3 and started just going because, like, we're just doing limits here. Let's talk about the situations. So again, some examples, like here, not quite a horizontal asymptote because we have a crossing, at least by the definition we would have used in like our Algebra 2 classroom. But as we go out to infinity, it's settled down along this horizontal line, right? Or you have your classic exponential function where we have a rational, oh my God, what did I just do? It's not what I meant to press. Go back. That's not where I want to go back to. This was. There, okay. Where we have our classic looking exponential function with the horizontal asymptote, right? This would be exponential decay, but like whatever. The weird one is we can have like this type of graph here. This is like a dampened harmonic function. So if you like think about graph dropping a ball and letting it bounce and hit the ground, and you're graphing the height of the ball, it's going to do one of these dampened harmonic motions where like the first bounce is big and the next bounce is smaller and smaller and smaller and smaller. So it's like oscillating up and down, but it's still settling down towards one value, right? So this thing, even though it's still bouncing up and down, up and down, up and down, up and down, the distance from that line y equals L is getting less and less and less each oscillation. So we can say that it's still going to L. Is everybody okay with that idea? So something like that does this is going to you'd surmise has to contain a sine or a cosine in it to some extent. Like 1 over x times sine x will have a graph that looks something like this. So we say we can do the same thing with negative infinities, right? Whatever, no big deal. We'll define if I have a limit that to either, a limit at infinity or negative infinity, and it exists, and it's a finite value, we're going to call that the horizontal asymptote. So our calculus definition of a horizontal asymptote is not the graph approaches but never crosses. Gone. Discard that from your knowledge base. Updated with the limit as x goes to infinity of f of x equals a finite value, or the limit as x goes to negative infinity of f of x equals some finite value. Can I get it limit happening at both ends that are different numbers? Yes. That just means you have two horizontal asymptotes. Can you get it happening at one end and not the other? Yes. Exponential functions work that way already. Can I have it happening on both ends? Yeah, rational functions operate like that already. Brooks.
So what it's saying is like, let's say that if x is going to infinity and then like it's becoming like closer and closer to 0, but it's not exactly 0, then the limit would be 0. That's what it's saying, right? Sorry.
Yeah, just like your exponential decay. Yeah. Everybody's okay? So slightly new, updated definition of horizontal asymptote. What's the advantage here? You can prove this, right? Did you have any way of proving something was a horizontal asymptote before? You just had to look at it and be like, well, it looks like it on the graph. Well, how do you know that, like, way out there someplace it doesn't cross and do something stupid, right? Like, it just goes, ah! You know, like, you don't know. There's no way to do that before. We do now, because we know how to do limits. And we can show that, yeah, that can't happen. Is it okay? Okay. So this is just an example of something that we have. If I look at the graph at tan inverse, you know, it looks like, you know, like an S, like a stretched out letter S. So I have a horizontal asymptote at negative pi over 2, and another horizontal asymptote at positive pi over 2. All right, where's my marker go? It's not a marker. Oops. You know, this is what your graph of tan inverse looks like, where you get two different horizontal asymptotes. So just wanting to remind you that, like, hey, you've already seen a function that has two different horizontal asymptotes before. You just didn't remember it because, like, woo, AP pre-calc, that was a blast. Like, I remember all of it, not like it sounded like it just got shoveled on top of me. But that's an example. If you talk about logistic functions, does AP pre-calc talk about logistics? That's like an exponential inside of a rational function. Okay. Those also have two horizontal asymptotes. I don't know if you talked about them or not. We do a little bit in regular pre-calc. Do you remember that? A little bit. You remember it was a word that we said. Yeah. That's enough. Yeah. All right. So, example, mostly just for the vocab piece. So it says, find the infinite limits, the limits at infinity, and the asymptotes for the function f, shown in the figure above. Infinite limits. Means that the limit to some finite value is positive or negative infinity, i.e., it's a vertical asymptote. Okay? Limit at infinity is the limit as x approaches positive or negative infinity of f of x. Not necessarily, because this can also be positive or negative infinity. To be a horizontal asymptote, or at a finite value anyway.
So what would it be like if as x goes to positive infinity, f of x goes to positive infinity? It'd just be
That's like the limit as x approaches infinity of x is positive infinity. No horizontal asymptote there, but that the limit at infinity is infinity, right?
okay.
Does that make sense on the subtle difference there?
Yeah.
So all of these are limits at infinity, but not every limit at infinity is a horizontal asymptote, right? Like one is a subset of the other.
It's like vertical asymptote and horizontal asymptote, like the infinity goes to f of x and then x goes.
One equals infinity and the other x approaches infinity.
Yeah.
But like your limits at infinity contain all horizontal asymptotes, but there's stuff that's not a horizontal asymptote that is a limit. Is everybody okay with the difference there? Just like squares and rectangles. Like every square is a rectangle, but not every rectangle is a square. You're all going, oh, I hated this part of geometry, please let's not go back.
Very interesting.
All right. So let's track this down then. Infinite limits, how many of those do you see?
2.
2, I agree. So this looks like the x-axis here, and this is the y-axis here. Nope, here. So my infinite limit, looks like I have 1 at -1. What does it equal?
Infinity.
Okay, positive infinity.
Mm-hmm.
So that means we have a VA at x equals -1. And then my second infinite limit was at, would you say? 2, I agree. And what's that limit equal?
Positive or negative. Why is it, well, it goes up to the Does that exist?
Why? Because the limit as x approaches 2 from the left of f of x is negative infinity, but the limit as x approaches 2 from the right of f of x is positive infinity. But we still have a VA at 2, because all we need is one side of it to go to infinity or negative infinity to be a vertical asymptote. Is everybody okay? This is like nitty-gritty definitional stuff. It's like, you know it when you see it. It's like, yeah, there's a vertical asymptote there. Yes, you know, the left-hand limit is negative infinity, right-hand limit is positive infinity. That means the regular limit doesn't exist because they didn't agree, and that's an easy spot to like scoot past, right? So again, vertical asymptote is left-hand limit is positive or negative infinity, right-hand limit positive negative infinity, or the overall limit is positive or negative infinity. Any one of those three is enough for a vertical asymptote. You don't need all of them. Cool? So limits at infinity, how many will you have every single time? 2, right? We'll have the limit as x goes to positive infinity, and the limit as x goes to negative infinity. So as x goes to positive infinity, I'm looking at like that. So the limit looks like it should be 4. And at negative infinity, it looks like that, 2. So it tells me then that I have an HA at y equals 4 and an HA at y equals 2. Do you like the color coding that I did here? Is that helpful in terms of like vocabbing it up here?
Yeah.
Because I know that's kind of precise. Do you guys have to go? If you have a pass, we'll see you later. Have a good meeting thing? Presentation?
Yeah. Thank you. Have a good rest of your day.
Yep. Check the video if you need it.
Yeah.
No problem.
Okay, maybe I'll sit at lunch. Alright. think you missed one.
You're welcome. All right. Here. Notice the limit is going to infinity or negative infinity, right? We've already talked about how to do this. Fastest growing thing, the top is a constant. The bottom is polynomial. Which one grows faster? The bottom, the polynomial. So this limit should go to infinity either way, right? Now, if we think about, if we remember our graph of 1 over x, we could be a little bit more precise where this is going to 0 from above. This one goes to 0 from below. If you think about it, we've used this example a bunch of times. Right, you're coming from the negative side up to 0. And this one is coming from the positive side down to 0. So you can do like that. If you don't need to by any means, but like if this is like part of something else, remembering to think about things that way would be helpful. I'm just pointing it out notationally what that would look like. You need to make an argument and write it down on a sheet of paper, but you could use words too. So this generalizes then that I can just take the limit as x approaches infinity of any x to the r, where r, or 1 over x to the r, where r is a rational number that's positive, and it's still going to be 0. Why does it need to be positive? Because a negative exponent makes a reciprocal, which would shift the x over r to the numerator. Now the rule is wrong, right? The second part says, well, if x goes to negative infinity, we have a bunch more words here. Why the heck do we need this? It says r is positive, rational number, such that x to the r is defined for all x. Why are we getting that extra little caveat there for negative infinity? What kind of powers of r do we have to be careful about? Remember, a rational exponent is the same as a radical. So if x is going to negative values, what kind of radicals are a problem? Even indexed ones, like square roots, 4th roots, 6th roots, 8th roots. Right? Because if you take the square root of a negative number, you get a imaginary result. You get an I. So all this is saying, all this extra caveat is like, if you're going to negative infinity, you better not be doing like a square root. You can't just like send that to 0, because you have like infinitely many undefined spots along the way. Like, it just doesn't make sense, right? Now, if that r is is a fraction with an odd denominator, doesn't matter, right? It's fine. Because you can take the odd root of any number, positive or negative. Everybody's cool? So that's all that's saying there. Again, like you see two almost identical things, and you're like, why does the negative, going to negative infinity, require this extra little gobbledygook here? And that's why, really. Okay. We've done this already. What's this limit? 3/5. Everybody agree? How do we do it?
Because they both have the same degree, so you take the coefficient.
Yeah, fastest growing thing on top is the 3x squared. Fastest growing thing on bottom is 3x squared. It's the same growth rate, x squared and x squared, so just leading coefficient over leading coefficient. You do your boo-boo bop-bop, and it's 3. I can't keep going. Full-on eats something, grapes, or I don't know. Does this feel okay?
Yeah.
Okay. I get a kind of a chuckle every time, so I'm going to just keep making the joke as long as you guys are laughing. I'm going to keep doing it all semester long, so beware. All right. Here it asks for the horizontal and vertical asymptotes for this. So the vertical asymptote should be easy, right? What is the vertical asymptote going to be? 5 over 3, right?
Real quick, for the last one, is 3/5 a slant asymptote, or is that
Horizontal.
Okay, cool.
Yep, horizontal.
So it's slant when 1 degree is higher than the other on top, right?
Correct.
Okay, cool.
And it could be any polynomial shape,
Yeah.
right? If the degree differs by 1, it's a straight line. If it differs by 2, it's like a quadratic. Like it's a parabolic asymptote. If it's cubic, it could be like, they get weird.
That's pretty cool.
Yeah, I know. Beyond the scope of what you need to do.
Mm-hmm.
But, okay. Yeah, so clearly we know how to deal with this, right? We have a VA of 5/3. To write that in calculus speech, you'd say the limit as x approaches 5/3 of this guy. Well, I can't just direct substitute it because I end up with like that 0 denominator, right? So I have to think about it a little bit. If this number is slightly bigger than 5/3, the bottom is going to be a positive value that's really close to 0. The top will be a positive value, right? Because you're squaring something, multiplying it by, and then adding something to it, so it's all positive, and then the square root of it's still going to be positive, right? So all positives, that's positive infinity then. Everybody okay? You just want to be careful, because if you write as x approaches 5/3, a thing is infinity, that's not technically correct. This is going to be does not exist, I think.
So, just go over again why you added the plus.
So I was going to look at either the right hand or left hand limit here,
Okay.
because I can't direct substitute and get an answer.
Yeah.
So I just picked, let's think about the right hand limit.
Okay.
So we're looking at a number just a little bit bigger than 5/3.
Okay.
3 times that bigger than 5/3 minus 5 is going to be positive, but really close to 0. The numerator, 2 times something squared plus 1, and then square rooted, all positive. Positive number over itty bitty positive number goes to positive infinity. Does that feel okay?
Yeah. So would you do it again to the left?
Nope.
Or just do it down?
All you need is one side of it going to infinity or negative infinity to prove a vertical asymptote. So I'm done. I've done enough calculus here. You could continue going on and do the left-hand limit, show it goes to negative infinity, and then say the limit and overall does not exist, but you don't need to do that. This is enough. Because the definition of a vertical asymptote is the left-hand limit is positive or negative infinity, or the right-hand limit is positive or negative infinity, or the overall limit is positive or negative infinity. Any or all of those will tell you the same thing. I'm just going to do the bare minimum of what I need to do to move on. You could do more and it's not wrong. But you don't need to. Good? Good question. You're welcome. To do the HA, I'm going to look at the limit as x goes to positive infinity. So I'm going to do a little bit of extra notation here, I think, to help explain things through. If we're going to infinity, does adding 1 or minusing 5 make any bit of difference to us at all? No. I can drop everything but the fastest growing terms. And just say that. Everybody's okay there? If I do that, I can reduce that radical, right? Everybody's okay? Because the square root of x squared is just x. So like, So I can say that y equals root 2 over 3 is one of my HAs. I need to check the other side, though, still. Because we can have two different ones, right? So I also need to check this side. And we'll do the same kind of thing, but I'm going to be a little bit more specific over here. And I'll explain why in a second. So we do the same thing, right? Start the same way. And I'm going to do the same thing. I'm going to reduce that radical. What do I get when I reduce that radical? So you want to say root 2x, right? Like, why is it different?
Yeah.
Well, this it's fine because x is a positive value. But here x is negative. If I take a negative number and I square it and then take the square root of it, what am I going to get? You get a positive result. If I take negative 1 and I square it, I get 1. And then I square root that, I get 1. It became positive. So what I'm really getting here is an absolute value. So remember, as an aside, when we defined the absolute value, you said it could be, we could define it this way, or probably at one point you defined it this way. That's what I used. Again, you're like, Mr. Cooley, that might have been an algebra 1. I'm supposed to remember that? Yeah, I think so. All right, well, why does that make a difference? If I'm plugging in this negative infinity, I have a positive value on top, but a negative value on bottom. So like I'm taking a positive x over a negative x, reducing values down, so I'm picking up a negative sign there. Woof, Mr. Kulik, that's absurdly tricky. I want to let you know, like that's very, very tricky. What's the best way to check something like this if you're doing it and you're not sure? Graph it and look at the picture, right? You'll catch if you drop the negative sign in there. You may not even really catch that, like, oh, there was an absolute value thing that I picked up that I didn't notice, but you'll see the negative when you look at the picture and see the two asymptotes, right? Like, that is okay. Like, again, much of your AP exam is going to be multiple choice. Half of it has a calculator attached to it. I would not expect something this tricky as a limit. Brooks?
So, how do you, this is just general about math, how do you find horizontal asymptote again? Like, how did you know it was square root 2 over 3? I think I just forgot.
Well, I did the limit, right? So if it reduces down, the limit of a constant is a constant. Okay. Right? The limit is x approaches whatever of a, it's just a. Because it's just a straight horizontal line. Right? It doesn't matter what x value you're going to, the y is the same thing. Is that okay?
Yeah.
Okay. All right. What about this guy? What's our nightmare here? Well, it's not a fraction, right? We have this limit to infinity, but it's not a fraction. All of our boo ba beep beep boo 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 requires a fraction, right? I don't have that. What are we going to do then? Well, it's going to be close to the same idea, right? Does the plus 1 matter? No, man. If we're going to infinity, that's fine. square root of x squared, since we're going to a positive value, can just be x Is that okay? Notice I never plugged the infinities in and never did infinity minus infinity. Right? I mean, technically I have like
Are you not supposed to?
infinity minus infinity is one of those indeterminate forms. Infinity minus infinity is not zero. I know. Now it was in this case because the growth of this and the growth of this are the same. But if I had e to the x minus x, those both go to infinity.
Yeah.
But their infinities are growing at different rates, so infinity minus infinity is an infinity.
Okay.
Yeah, I know. There.
So when it's not a fraction, then you can't just take, or you can take the highest growing value, or like you just look at the two.
You have to really think about the growth rates. Like you drop everything but the highest growing term in each chunk, right? And then you try to reduce it down as best you can and cross your fingers and hope you're not going to get two different growth rating things where you can do something like this.
So like if it were square root of like x to the fourth, then that would.
When you get to there,
I mean.
yeah. So let's do it. Let's do it. Right? This is a good what if question. Right? So I would start the same way. Infinity x squared minus x. And now, what I would think about here is I would do this. Factor an x off. And then I can use my limit law to say that this so I can do that. That's infinity. That's infinity. Infinity times infinity is not indeterminate. That's just infinity.
Okay.
So, depends is the answer. Like, well, if that's x to the fourth, well, that one I can do.
Yeah.
And as long as it's like, I kind of feel it out a little bit.
Okay.
The big takeaway, though, is, where was that at? Was that in 2, 3? Where did we list? No, I think it was here. We wrote them all down somewhere. No, maybe it was in this one. Is it in this one? I have it written down somewhere, those indeterminate forms. Where did they go?
It was like the first.
There they are. There we go. Like, we got to have these. Like, you got to see those and know, like, this is not telling me anything. Like, go back and look for another algebraic workaround. Eventually, we're going to get, like, the fix-it-felix hammer to deal with these things, but we have to do a lot more before we're at that point. But this becomes much less of a hassle really quickly. Well, it's still kind of a hassle, but, like, it's every problem is a nail, and this is our hammer. We're going to do them all kind of the same way, but, like, might require a little bit of, like, finagling to get it to where we can hammer it, but eventually these become easier. But those are the 7 we got to be careful about when running into. Now, in all reality, I wouldn't expect to see anything past the first 4. Those other ones at the end, I would not expect to really see in an AP classroom, but there are 7. Sarah?
Is it infinity? Just
Yes.
okay.
Yes. Emma.
Nice enough.
Of course. Lucia.
So whenever like we were told that like anything with the 0 power is 1
Except for 0.
or infinity.
Or infinity. Yeah. Sam.
I just then.
Oh, yeah, of course. And if you think about like why 0 to the 0 isn't 1, right? Think about how we defined this, right? That should be 1, right? You agree? This is the same thing as a to the n minus n, right?
Which is a to the 0.
Which is a to the 0, so that should be 1. But what happens if a is equal to 0? You're dividing by 0, right? That can't be 1, right? That doesn't make sense. Does that feel okay?
Yeah, that helps.
Okay. All right. Did I see hand? No? Sam, you good? Okay. All right. So, let's see here. Let's look at this one. This is a good one. Oh, I got half an hour left. I'm doing great. Yeah, doing great.
So arctan is just
Tan inverse.
right?
Exactly. So if I try to direct substitute this,
0.
It's not gonna work.
it's going to go to positive. The inside goes to positive infinity, right?
Oh wait, it's
2 minus
1 over 0. Dragging this up to 0.
If I look at this, I'm going to have something a little bit bigger than 2.
No, exactly.
So when I subtract 2 from it, I'm going to get a number, positive value, really small, really close to 0, over 1. That's going to positive infinity just like before, right? You see that? Again, that's just me looking at the inside part. So I'm going to use this and going to rewrite this as then and I guess let's do this. You guys hate it when I abuse the x value or the x variable. So I'm just going to rewrite it like that to simplify things down, right? If the inside part is going to positive infinity, let's just rewrite this as like y goes to positive infinity, arctan y. Is that okay? And the reason I want to do that is I have no stinking idea what that picture looks like. Couldn't tell you. Don't know. Arctan, I know what that graph looks like.
Are we supposed to know what it looks like?
Ideally. Now, again, like our textbook that we use is very trig heavy on it, especially like trig heavy on these like stuff, facts like this. The AP exam is not going to be this nasty as far as like remember all this specific, really hyper specific trig things. I will not be that nasty to give this to you on a non-calculator section to where you can't just like type in tan inverse into a graph and look at the picture. But like, this is what you do if you had to do this in a calculator. Is I'm relying on remembering this picture because if you think about the one period of tangent, looks like this, right? Right? One period of tangent looks like that. So this guy becomes a horizontal asymptote, this guy becomes a vertical or another horizontal asymptote, and then I like flip it across the line y equals x. So that's what I'm trying, that's what I'm remembering. Is that, I know that's hard. But this is the point. That's y goes to positive infinity of arctan. I know. You don't have to look happy about that. You shouldn't. You shouldn't feel happy about that. But that's what's happening. So it's the not knowing the trig that's the confusing part, right? This idea of like I have a function of an infinity, and I don't really know how to deal with that, where I'm going to do a substitution and try to simplify this out. Like, I don't know what the blazes this graph is going to look like in my head. I have no chance on that. But if I rewrite it with a new variable, where I've changed, notice the inside goes to infinity, so I'll just take the limit of going to infinity of just the outside of a single variable. This, I have a chance of coming up with the graph. Right? That I have a prayer, because at one point I should have known this. I recognize that as something like, we probably graphed this in class before. I just learned it for a day, because I figured, it'll be okay. And it's like, this is that day that I thought it wouldn't come, and here it is. So, Brooks.
I was just a bit confused, so I put inverse tan of that equation into Desmos, and it just looks like that, like as x approaches 2 from the right hand side, it looks like it goes to like pi over 2. Why does it say it goes to infinity?
That's why I don't want any part of this guy.
Okay.
That's why I don't want any part of that. That's like, I just don't even know what the graph of that's supposed to look like. I have a feeling that if you graph that, the computer is going to have problems like coming up with a good enough resolution image, because there's probably going to have a lot of erratic behavior going on. But I can do these substitutions, and I know what this graph looks like without having to go to the computer.
Okay.
So a lot of times, just like even some of these things that look relatively simple, your graphing software is going to have a hard time, like what is in like getting close enough to like, it just kind of breaks it.
I was just confused because it's like, if it's a little bit bigger than 2, then it's going to be like 1 over a really small number. Wouldn't that be 1? Or
So if I have like 1 over 1, that's 1.
Yeah.
1 over 0.1 is 10. 1 over 0.01 is 100.
also
1 over 0.001 is 1,000. So it's blowing up to positive infinity. The closer that gets to 0.
Never mind. Okay.
Does that make sense? You always forget about like the stuff between 0 and 1.
Yeah.
It's like I forget it. Yeah, those guys don't matter. So it does the opposite of what I expected to do.
Thank you.
Yeah. So this guy here, again, if I try plugging the 0 directly, what's going to happen? I get an infinity or negative infinity up there, right? I get 1 over 0. So I'm going to do it the same way. So I'm going to take the limit of the inside. Now this is going to be a slightly negative number, right? So this is going to go to negative infinity. So I'm going to take this then and replace it and write it as the limit as x goes, let's use a y, to negative infinity of e to the y.
Why do you use y?
I don't know, it feels like you guys yelled at me when I tried to just use x's over and over again. Like I'm just changing, like I'm replacing this stuff with a y.
Does it matter
What letter you use?
Yeah.
No, you can use x again. It's fine.
Okay.
Yeah.
I just
It's-
felt like why has something to do with it?
Oh.
Or the axis and I'm. Yeah, me
No.
too.
No, I'm just,
Supposed to do the y
no y-axis. Just like I'm making a variable. You call it any letter you t,
Okay.
right? Like not associated with any axis at all.
Okay.
Unless you're thinking about parametric things, and the t is the thing, the parameter there. Call it a q. Nothing's q. Brooks.
When you wrote the new limit, where did e go?
So what I did is I looked at, give me a different color. I looked at doing, oops. I pushed the limit inside the composition.
Yeah.
And then I'm just worried about that inner part. That's what I'm trying to do. I did the same thing on the previous one.
Okay, so then you kind of like discard e because it's not born right now.
Well, I figured out that inner limit. Exactly.
Okay.
Because I can't write e to the negative infinity. That's bad notation. Even though that's kind of what we're doing here. So the limit as y goes to negative infinity of e to the y. What kind of number is going to be in the exponent? A negative, right? So this is really going to be the same as the limit as z goes to positive infinity of 1 over e to the z. I'll change another letter for
You
you.
keep switching the letters.
Well, I did another substitution.
Okay.
And now this is clearly 0, right?
Oh, a little bit. Y is 1 over x, correct?
Yes.
Okay. Yeah. Okay.
Wait, why did you do positive?
So you'd agree that if I take this, that's the same thing, right? If I just push the sign onto the variable, it's the same thing, right?
Yeah.
So I'm doing that. Does that feel better?
Yeah,
Okay. Yeah, if it doesn't make sense with what I did, stop me and push me on it, and I'll try to write it another way, and maybe fill in some more gaps. If it doesn't work for you, say something. I'm glad you did.
So I could write what you just wrote, like e to the negative y, and then it's still be inside of it.
It's fine to do that. Yes, absolutely. Yeah, you can just keep it all, you use x's the whole way through if you want. Like, I don't mind you being, like, abusing and just using x over and over again, and they're like, different x's. Like, that's really common. Like, you'll see that in textbooks all the time. That's okay. All right. So, up to this point, we've seen that these infinite limits always exist, right? Because there's not really left hand and right hand side to disagree. So far, so good? Well, there's one other reason why a limit might not exist. If I'm looking at the graph of sine as x goes to infinity, the graph of sine looks like this, right? Oh, come on now. Is that settling down to any value? So what would we say here? And the reason is it just oscillates, right? And that oscillation isn't getting smaller and smaller and smaller like we saw in the graphical example before when I talked about the ball bouncing on the ground. Here, the oscillation is still staying the same, right? It's like the tides. You know, like water comes in, water comes out, it doesn't ever slow down. I mean, I think technically it is, but it's at a scale where it's like unnoticeable. Because I think eventually we're going to lose the moon. Like eventually the moon's getting further and further away where it's going to escape our orbit.
Really?
Yeah, it's like.
You're talking about like billions of years.
Oh, so
Like-
now we're here.
No.
I was like, damn.
Why isn't this a news story?
When is this happening?
Yeah, it's tomorrow. The moon gone. No.
That was away for like 3 centimeters.
I'm not gonna
Yeah, something like that. Yeah. Yeah, it's like we're losing it. Like it's getting a centimeter further away every year or something stupid like that. Like it's not going anywhere. In our lifetime, our children's to the 10th power lifetime.
Wow.
You know, like that thing ain't going anywhere.
Stop that point, Meredith.
Worth noting here, I have to be a little bit careful if I have a limit to infinity of a polynomial because the degree matters a little bit. Because I remember a negative number to an odd power is negative. A negative power to an even power is positive. So again, this one would just be like positive infinity, but that one would be like negative infinity.
Simple.
Which again should make sense if you think about what the graph looks like, right? The graph of x cubed is just like, whoop, where the left end points down, the right end points up. Negative infinity as x approaches negative infinity, positive infinity when x approaches positive. Everybody's okay? What's the other thing you also have to consider? the leading coefficient, right? Because if I, stick that one on there, it flips. Everybody's okay? I don't know. Okay. We actually did this, right? When Meredith asked, what if it was x to the fourth? Look, it happened. So I'm not going to do that one again because it was already included in your example from before. You're like, what if it did this? It was a great question because we're going to do it anyway. You're welcome. What's this one going to be? This one you should be able to boo-boo bobble.
Either non-existent.
Well, it's going to be positive or negative infinity, right? Why is it negative, Meredith? You are right. Why is it not positive?
Because the exponement's bigger on the top, so then it's just the bottom is negative.
No, the x is negative on the bottom.
Yeah.
So if I have a positive over negative, that's going to be negative. Right? So just look at the two biggest things.
You struggle to get that out.
But
She knew it. She knew it. It's like I can't articulate why, but I know that's the answer. You were right on it. Like I didn't even hesitate. You're like negative infinity. I was like, all right.
it is a slant asymptote.
It is, yes, because the difference in them is degree 1. So if you did the polynomial division, you get y equals negative
Yeah.
x plus something.
Yeah.
Yep. Our last guy asks us to sketch the graph of this thing by finding its intercepts and its limits. Okay. Well, let's start with the intercepts. What are the x-intercepts for this going to be?
2.
Okay. 2, -1, and 1. Okay, what about the y-intercept? So zeros everywhere, right?
0.
So 2 to the 4th
It bounces.
times 1
Yeah.
times -1. So that would be -16, I think.
It just bounces off the x-axis and 2 is all I know.
Great. So how did you know that we have a bounce at 2?
Because it's a even.
Even degree. So we have a bounce.
And it goes through it. 1.
And we have, how does it pass through at 1? If it's a degree 1, it's going to be like a straight. So it's just going to go like pass kind of straight through. It's got to go pick this guy up. And then what's it going to do at?
It's going to do a degree 3 thing, so it's going to go through it.
Yeah, it's going to be a bend. Yeah, it's going to be a squiggly one. Yep. I'm always bad at it.
For that.
Yeah, I call it a bend,
No.
where it changes concavity. So
There's no scientific name for it.
that's what I've seen it in the textbooks called as well.
Okay.
And then what degree is this polynomial in total?
4.
8. 3 or 4 plus 3 plus 1. So it's either going to be both up or both down. The leading coefficient is positive, so that both ends point up. So that was our limits as x approaches positive, negative, infinity. We just used what we knew about polynomials rather than worrying about that. Feel okay?
Yeah.
This is the homework. We're not going to do a homework quiz on this next time.
Good.
So we've done 3 already. You guys feel like you're stressed out enough? We'll take a little break. I'll save a homework quiz for with the section when we start the new stuff. Next class, we're going to talk about the test format and do some light review stuff. So I am currently in the process of writing this chapter 1 test. At one point last year, I lost like all of my files from like the past 2 or 3 years, including on my chapter 1 test. So I'm starting that over from whole cloth, which is lovely when you want to make like a bunch of different versions of it potentially. But I will say, I have my stuff up about what was on there last time. So you will have multiple choice questions in the style of like an AP multiple choice question. I went through and picked out ones that I thought were pretty good. We'll do some practice on them in class on the review day. We'll get on the MyAP site and have you guys answer some just to get a feel for that. I put a bunch of them here if you want to look and start on stuff. There are going to be 10. The answers for everything are listed here also. I have the test description from last year. It's not going to meet exactly this. Like the topics are probably good, but like these specific formats, I haven't finished that yet. When I do, I'll have it done by next class and be able to talk about it in detail, about what to expect. But there will be, half of the test will be calculator, the other half will be no calculator. It'll be divided into 2 separate like packets. You turn one half in, pick up the other half in your calculator. So the hardest thing for students tends to be their time management. When they know they can't go back to the first half, but sometimes you just gotta let that go. So you leave yourself enough time to work on the second half. Unfortunately, it's not the situation where like you can just start by doing everything you know first, and then circling back and doing the stuff you don't know how to do. This is the half you can do, and then try to give yourself enough time for the other half. I'll make it clear as to like the division of problems. Sometimes it's pretty evenly stacked. Sometimes one section should easily take longer than the other. But I'll always do something like this for you guys in terms of what to expect. Lucia? Sure. So if you're looking to start looking over things and preparing a little bit, you know, like the homeworks, if it was real hard in the homework, probably not something that I would put on a test. So if it's like, this was like a ridiculously difficult homework problem, that's not a test question. That's a great enrichment problem, and I love to give things that like bring in other aspects or tie things together or force you to think about it in an unexpected way using our language of calculus. Those are great questions, and I think they really add something. They're not appropriate time test questions. They're appropriate, like, you have 2 questions, you have 4 hours. Here you go, which is like what happens in grad school. Or even worse, here's 2 questions, you have a week, you can use whatever you want. Like, have fun. Those are the worst, that's the worst test format, believe it or not, because it's gonna be just incredibly difficult. The best test format is timed, closed everything, because I know it has to be doable without like an incredible insight. The other way, it's like, this is gonna be something where I'm really gonna have to think hard on this for a long time. Like, it's literally gonna take like 10 hours of thinking before I really even write much down, before I come to anything good. The in-class is never that way. And I don't want it to be that way here either. Like, I want to give you stuff that you've seen before, or it's like just a version of something you've seen before, a familiar presentation, nothing cuckoo crazy. Or if it's an unfamiliar situation, it's just that I peeled off some of the group work that you have to do it, where it's just trying to make it like, boil it down to its essence. Like, ask you an IPT question where I've given you like a table of values for the function, right? Where all you need to do now is like pull the right values from the table to use as your upper and lower bounds, and you're done, basically, right? You just have to write some stuff. So it really is just checking to see if you know how to use the IVT to write something. I've taken away the hunt for like, you need to find something above and below, especially in a no calculator section, like, get rid of that trash, like nobody has time for that without a calculator. So even if it's like an unfamiliar presentation, it's usually just trying to make the question easier, boiling it down to its core idea. So again, I try to be really mindful about, you have 80 minutes, that's it. That I don't want you to have to feel like you stay over and over and over, or like, I didn't have enough time to do this, I want it to be something that's like realistic to do. That being said, there are things that like need to be done, be able to be done quickly. So like, if you have a boo boo question, like that's one you should be able to do quickly. Right? You should be able to look at that and almost write down an answer inside of 10 seconds. Like look at it carefully, but like there's nothing to write down, really. Or not much. Like more than one step would be pushing it. Right? So, you know, like just make sure you're not wasting time on stuff that like you should be able to do. Or if it is a difficult question, oftentimes I'll include it to like get you started on the first step. Like if I give you a squeeze theorem limit, where like you have to build your own inequality, I might give you the first step of the inequality. Right? Like start with this. You know, and then it should usually be much easier once you have a starting point to build one of those. You know, so like I try to not make this like you have to have every nitty-gritty detail. I want to try to boil it down to like big ideas and like can you get most of the way there, especially if I give you a push in the right direction. Does that make any sense? So we'll do like our normal review day. We'll do some of the 8 multiple choice AP practice. The next class will start the topics for test 2. And then the following class will be the test 1. So test 1 would just be covering 2.2, 2.3, 2.5, 2.6, and then like that bonus composition thing that we did. Brooks?
I just had a little random question about like physics and math. If that was okay.
Sure, let's hear it.
Like, what would happen theoretically if like you went faster than the speed of light? Like, would you just like not exist anymore, or what would happen?
Well,
sorry, I was just thinking.
yeah, from a physics standpoint, I think that at the speed of light, time stops and you become a singularity. You become like a single point mass. So you have like infinite density.
Oh my gosh, you become a black hole.
Essentially, I think. So I don't know what would happen if somehow you were able to violate that, what the consequence would be.
Okay.
Like relatively, your time would stop for you.
Would like everything like around you would like stop as like time would be frozen? Or?
Everything around you relatively would look stationary.
Okay.
Because you're moving relatively so much faster.
Good afternoon, Notre Dame crowd. Let us end this day in prayer.
Right, like.
In the name of the Father, and of the Son, and of the Holy Spirit. Amen. Where do I need to trust in the Lord today? Isaiah chapter 26, verse 4 says, "Trust in the Lord forever, for the Lord is the rock eternal." Amen. In the name of the Father, and of the Son, and of the Holy Spirit. Amen. Students, have a great rest of your day. Teachers, you may dismiss at your ready.
Bye, guys. Have a good day. Was today okay? This was good? Yeah. This is how the end of these blocks should go. Like, it's rough in the beginning, it gets to the middle, and it's like, well, I don't think I can do it. And like, it starts clicking in, and by the end, it's like the last section is not the worst section. And you go back and look at the first step, you're like, you say, why didn't this hard?
Yeah.
Because now you have all the tools that you need to make those problems easier. You just make it not easy. Not fully are.
Yeah.
You're welcome.
Thank you.
Have a good day.
You too.